Hey everyone! In this video, I'd like to do another related rate example. And in this example, we are going to be using triangles again, but in this case, we're going to have to use trigonometry to help us solve this. So let's take a look at the example. It says, two cars are traveling to the same destination. The yellow car is traveling east away from an intersection at a rate of 60 miles an hour. The white car is traveling south towards the same intersection at a rate of 40 miles an hour. Let x be the distance between the yellow car and the intersection. Let y be the distance between the white car and the intersection at time t. Let theta be the angle at the yellow car and opposite side y. And we want to find the rate of change of theta in radians per hour when x is 8 and y is 6. Okay, there's a lot of information going on here. So let's start with the diagram. We can label that with what we know, and hopefully that'll help us guide our problem solving process. So we have an intersection. One of the cars is traveling south towards the intersection. The other one is traveling east away from the intersection. I can represent that entire situation with a triangle. So let's say here's our intersection. One car is moving east away from that. One car is moving south towards that intersection. And we can create our triangle. So moving east away, this is our yellow car. And then moving south towards the intersection is our white car. It says let x be the distance between the yellow car and the intersection. So our horizontal piece here is x. Let y be the distance between the white car and the intersection. So this vertical one is y. And it says let theta be the angle at the yellow car and opposite y. So our angle here, this one is theta. Okay, we know that x is 8 miles, and we know that y, this is going to be 6 miles. And while we're at it here, we could also figure out our hypotenuse. So using Pythagorean theorem, or 6, 8, 10, that is a Pythagorean triple. So our hypotenuse here is also going to be 10 miles, so we know that as well. Now we also know some rates of change. So the yellow car is traveling east away from the intersection at a rate of 60 miles an hour. So the rate of change of x with respect to time, this is 60 miles per hour. And it says that the rate of change for the white car is traveling south at 40 miles an hour. So the rate of change of y with respect to time, well, it's moving closer to the intersection, so that distance is shrinking. So this is actually negative 40 miles per hour. All right, so I think that's everything that we know. The next thing we need is an equation that's going to relate together all of our variables. We want to find the rate of change of theta. So we need to relate theta to x and to y. We can do that with trig. So in relation to theta, y is our opposite side, x is the adjacent side. We can use tangent to relate all of those together. So the tangent of our angle theta is equal to y over x. All right, so we have everything we need. The next step is we're going to take the equation that relates all of our variables together, and we're going to differentiate that with respect to time. So on the left-hand side, the derivative of tangent, that's equal to secant squared of theta. And this will be times d theta over d time. On the other side of the equal sign, we have y over x. So we're going to need to use our quotient rule. So we have x times the derivative of the numerator minus the derivative of the denominator times y, and this is all over x squared. All right, so a lot going on in this equation, but luckily for us, we can substitute in a lot of things. The first thing I do want to start with is I want to substitute something in for secant squared. Now, the secant squared, that is equal to the hypotenuse divided by the adjacent side. So secant of theta is equal to 10 over 8. And if we simplify that, we know that it's 5 over 4. So that means that the secant squared of theta is equal to 5 over 4 squared, which if I square the top and the bottom, we end up with 25 over 16. So with that information, we can substitute 25 over 16 for the secant squared. So that's going to help us out a bit. So secant squared of theta is equal to 25 over 16. We have d theta over the derivative of the time. This is the rate of change that we actually want to solve for, the rate of change of theta. On the other side of the equal sign, let's see what we can plug in. So we know x is 8. The rate of change of y, this was negative 40 miles an hour. The rate of change of x was 60 miles an hour. And we know y is equal to 6. And this is all divided by x was 8 squared. Okay, I'm going to move up here and let's do a little bit of simplifying. So we have 25 over 16 times the rate of change of theta. 8 times negative 40 is negative 320. And then 60 times 6 is minus 360 over 8 squared, which is 64. 25 over 16 times the rate of change of theta. We have negative 320 minus 360 is negative 680 over 64. And now multiplying both sides by the reciprocal of this fraction, I'm going to multiply by 16 over 25. And let's see what we end up with. So our rate of change of theta with respect to time, 16 over 64, that simplifies to 1 over 4. So we get negative 680, and 4 times 25, we get 100. So negative 680 divided by 100, we get negative 6.8 radians per hour. So here's our solution. So our rates of change directly tied to each other. So in this case, we have 3 rates of change. We have the rate of change for the white car, the rate of change for the yellow car. As the white car gets closer to the intersection and as the yellow car gets further away from the intersection, the angle that these two cars are forming is shrinking. And it's shrinking at a rate of negative 6.8 radians per hour.